Now we'll talk about counters. A register that goes through a prescribed sequence of states upon the application of input pulses is called a counter. Digital counters are electronic devices that perform a variety of counting functions. The asynchronous counters. The term asynchronous refers to events that do not have a fixed time relationships with each other and generally don't occur at the same time. An asynchronous counter is one in which all flip-flops within the counter don't change states at exactly the same time because they don't have a common clock pulse. Another term for these counters is ripple counters. A binary ripple counter consists of a series connection of complementing flip-flops, with the output of each flip-flop connected to the C input of the next higher order flip-flop. The flip-flop holding the least significant bit receives the incoming count pulses. A binary counter with a reverse count is called a binary countdown counter. In a countdown counter, the binary count is decremented by 1 with every input count pulse. Now the BCD ripple counter. A decimal counter follows a sequence of 10 states and returns to 0 after the count of 9. Such counter must have at least 4 flip-flops to represent each decimal digit, since a decimal digit is represented by a binary code with at least 4 bits. The operations of the counters can be explained by a list of conditions for flip-flop transitions. When the C input goes from 1 to 0, the flip-flop is set if J is equal to 1, is cleared if K is equal to 1, is complemented if J is equal to K and is equal to 1, and is left unchanged if J is equal to K and is equal to 0. The synchronous counters. Synchronous counters are different from ripple counters in that clock pulses are applied to the inputs of all flip-flops. A common clock triggers all flip-flops simultaneously, rather than one at a time in succession as in ripple counters. The design of a synchronous binary counter is so simple that there is no need to go through a sequential logic design process. In a synchronous binary counter, the flip-flop in the least significant position is complemented with every pulse. A flip-flop in any other position is complemented when all the bits in the lower significant positions are equal to 1. Synchronous binary counters have a regular pattern and can be constructed with complementing flip-flops and gates. The C input of all flip-flops are connected to a common clock. The chain of AND gates generates the required logic for the J and K inputs in each stage. The counter can be extended to any number of stages, with each stage having an additional flip-flop and an AND gate that gives an output of 1 if all previous flip-flops outputs are 1. An opt-out binary counter is a counter that can be constructed except that the inputs to the AND gates must come from the complemented outputs, instead of the normal outputs of the previous flip-flops. The two operations can be combined in one circuit to form a counter capable of counting either up or down. It has an up control input and a down control input. When the up input is 1, the circuit counts up, since the T inputs receive their signals from their values of the previous normal outputs of the flip-flops. When the down input is 1 and the up input is 0, the circuit counts down, since the complemented outputs of the previous flip-flops are applied to the T inputs. When the up and down inputs are both 0, the circuit does not change state and remains in the same count. When the up and down inputs are both 1, the circuit counts up. This set of conditions ensures that only one operation is performed at any given time. Here we can have the graphical description of an up-down counter. Now a BCD counter. A BCD counter counts in binary coded decimal from 0000 to 1001 and back to 0000. Because of the return to 0 after a count of 9, A BCD counter does not have a regular pattern, unlike a straight binary count. To derive the circuit of a BCD synchronous counter, it is necessary to go through a sequential circuit design procedure. The input conditions for the T flip-flops are obtained from the present and next state. Also shown in the table is an output Y, which is equal to 1 when the present state is 1001. In this way, Y can enable the count of the next higher significant decade, while the same pulse switches the present decade from 1001 to 0000. The flip-flop input equation can be simplified by means of maps. But first, we will need to see the table. And here we have the table for the BCD counter. Then the unused states or minterms 10 to 15 are taken as don't care terms. The simplified functions are tq1 is equal to 1, tq2 is equal to q8 q1, tq4 is equal to q2 q1, tq8 is equal to q8 q1 plus q4 q2 q1, and then y will be equal to q8 q1. The circuit can easily be drawn with 4 T flip-flops, 5 AND gates,